Good morning, everyone. Welcome to the sixth lecture of the workshop of PWF Sudan, Expanding Horizons in Physics in Sudan, second edition, about the density function theory methods and applications. Today's lecture will be given by Dr. Alberto Carta, a computational scientist at PSI in Switzerland, PSI Institute. We'll be talking about the basic DFT calculations, band structure. Welcome, Dr. Alberto Carta, and the stage is yours. You can share your screen now.
Yes, sir. You need to unshare yours, and then I can. Okay. Entire screen. Let's do entire screen. Okay. Can everyone see my screen?
Yes.
Let me close this. Okay, so I cannot see directly the Zoom lecture. Okay, so please block me. Okay, if I get tangled in something and I don't see you. Okay.
Okay.
Okay. So welcome everyone. So this lecture is going to be. This is the first time for me teaching about this particular topic. Okay, so it's new for you, but also it's new also for me. And then so feel free to stop me at any point that you might see fit. Okay, so like if you don't understand something, whether it's from like the language that I have to use, so like basically if you want to ask me to use like simpler language in explaining things, or like you don't understand the concept, please block me immediately. Okay, so I will not have at the end of the lecture like a question session. I would much rather prefer that we stop and then we talk about the things that you don't understand as they come. Okay, so now, so my objective here is, so like we have around 3 hours. Okay, so my objective here is to do around 50 minutes, then stop, 10 minutes coffee break, then 50 minutes again, then stop again, and then again a last session of 50 minutes, so that like we keep the attention going. So let's start a little bit by introducing the topic. So my understanding is that you got already some solid states and some density functional theory, some small amount of density functional theory. Okay, so like the objective of this lecture is to really bring these things together, okay, and give you some ideas, some practical aspects of what happens when someone wants to use density functional theory to work on real systems. Okay, so we are going basically to look at 4 topics here. The first thing is we're going to look at the physics of free electrons in solids, okay, and look at the concept of density of states. Okay, then we're going to look at the concept of band structure and Bloch theorem. And these two are not necessarily topics that are unique to DFT, but they're gonna be useful in for what we are going to do later. Then we are going to basically do. Hopefully, like we get through this in the first hour. Then we are going to go to density functional theory, solving the Kohn-Sham equation, and I'm going to give you some introduction about the code that you guys are going to be using in the tutorials, or in all of this. In all of the tutorials, which is Quantum ESPRESSO. And hopefully, like if we have some time, we are also going to give you some flavor of what other codes are there in order to perform these calculations in practice. And then, like at the end, we're gonna try to bring it all together. And if we get some time, I'm gonna show you like some calculations live. If we don't have time, it's not super necessary. You're going to do it on your own. But if we see that we have, like, as I say, half an hour at the end, I can show you a little bit some calculations in front of you. Okay, so let's start by like a concept, by the concept of the physics of free electrons and the concept of density of states. So the idea here is like I have adapted these slides from beautiful slides of Shobana from the Jawahar Nehru Institute in Bangalore. Okay, so it's so like the lecture will follow that flow. So before starting to delve into the Consham equations, I would like to have some interaction with the class, okay? So also to understand what you have learned in the past week. So let's have a quick recall of what happens for free electrons, okay? So this is basics quantum mechanics. And then I want to ask the class, for instance, a couple questions. So the first question that I would like to ask is, what is the solution of the Schrödinger equation for free electrons when we have no potential in the material? And then I want like also to ask what are the energies that are associated with these free electrons? What kind of like in terms of quantum what quantum numbers are good quantum numbers to describe free electrons? And then if we think about eigenenergies, about the energies of the Schrödinger equation, we also think about eigenfunctions. So like what functions solve the Schrödinger equation for a free electron? Maybe we can give here like a couple minutes for people to answer. So if someone can raise your hand, I think Ala and Abu Bakr can moderate.
Wave function.
Sorry?
Yes, Qutayba, you
Wave
can
function.
raise your voice, please. Qutayba.
Sorry, I have a problem with my device. The solution of Schrödinger equation is a wave function. Sine or cosine.
Sine, okay. So wave function is the general term. Okay, I understand what you mean, but wave function is a general term for the equation. But like, I mean, I think I know what I think I understand what you mean. You mean that these are like they are waves, right? Like waves. Is this what you're meaning?
Yes.
Yes. Okay. Perfect. So and so one thing that I can ask about the energies is what energy what are the energies of these waves? So is it like a continuum of energies, or are they quantized? So do you have discrete states, or do you have a continuum of states for these plane waves?
Quantized energy.
I mean, okay, yes. So this is unfortunately incorrect in the sense that so for free electrons, actually there is no confining potential. Okay, so you start having quantization of waves when you start confining electrons into something. But for free electrons, we actually have a continuum of waves that can exist. Okay, so let's start from here. So like let's start from the energies. So like in a free electron state, energies depend on something called a wave vector. Okay, so we have a direction with some magnitude. Okay, and this is like a wave vector in what is called reciprocal space. You should have done this with Natasha last week, and so the idea here is that you don't have really a quantization because you don't have this confining potential. So the electrons are free to exist at every energy, at every energy, and the energy of each electron is given by its wave vector, and of course it's dependent on the Planck constant, and it's dependent also on the mass of the electron. Okay, so if we look at systems, so whenever we think about quantum system, we need to think about dimensionality. Okay, so we need to think about whether we are living in 1D space, in 2D space, or in 3D space. And so in 1D space, this kind of formula, basically what it means that the electrons, the energy of the electrons behave like a parabola. Okay, and in 2D space, we have two directions in which you can move. And so this becomes really like a paraboloid. So this means it's a parabola that you can rotate around an axis. And so it becomes this kind of bowl-shaped dispersion. And then in 3D, you can also have basically it's the same. It's the same for three dimension. As your colleague pointed out, the electron wave function in free space are called plane waves. Okay, so these so the wave function generally we indicate with psi, and the plane waves are simple sines and cosines, or in case of so what we generally use for this kind of calculations to make things simpler is that we use a complex exponential, so e to the I kr, where k is the wave vector that we have here, and this basically determines the direction and the direction of the wave, and then r is just like some vector in some vector in real space. So the important thing here is that generally we simulate these we simulate our calculations on a normalized box of some volume v. Okay, and within this box, all of these plane waves form a complete orthonormal basis. Okay, so this basically means that orthonormal basis is some complicated way to just say that you can describe everything that happens within our simulation box as a combination, so as a sum and product, as a sums of a linear combination, as a sum of these basis function, which are plane waves. Okay, so now I want to give an idea of the concept of density of states, and this is like some summary of the thing that we're going to derive in the next step. But then maybe I want to ask the class if you have if you guys have some feeling for what it means. What a density of state means. Okay, so like, do you please feel free to chip in and then say, okay, so if you have ever seen this concept, and if what your understanding of this concept is. I'll give you like 1 minute.
I think I mean a number of electrons in some level of on some state.
Can you repeat? Can you repeat?
Number of electrons for some state of for some level, like I think that.
I think this is okay. So this is almost correct in the sense that so given one like a state at a particular energy, okay, how many available states you get at that energy is the density of state. So basically this means it's not necessarily the number of electrons, even though at some point you will occupy these states with electrons, but it's really the number of available states that you have at a given energy. Okay, so for example, if you look at the hydrogen atom, at a given energy you don't have only one state, you have two. Okay, you have spin up and you have spin down, for instance. Okay, so this is kind of the same. This is kind of the same here. So when you start looking at solids at a given energy, you're not going to have one single state. You're going to have like a bunch of them, and the density of states is the quantity that counts the states at an available energy. So this delta function that you see here, this is a Dirac delta, but it's just a complicated way to say, count please at a given k vector, at a given wave vector, count me the number of states at energy E identical to the energy of that k vector. Okay. So, and the point here is that I want to convey to you is that depending on the dimension that we have of the system, this density of states is going to change. Okay, so and it's going to basically, so the dimensionality of the system, whether we look at like a molecule, so like something that is a 0D system, if you wish, and then we start adding the dimension to the system. So we're looking at 1D system, 2D system, or 3D system. We are going to get a different trends for the density of states. So the first thing that I want to basically show you is like we're going to look at one of these cases, and maybe this is the one that is the most important and the most relevant for what we're going to do next, is density of states for a generic three-dimensional system. Okay, so here we're going to look at the electron gas in 3 dimension. Okay, so as I said before, we are simulating whenever we look at like any realistic material. When we do simulations, we generally have like a box of site L that we are simulating into. Okay, so the idea is that let's imagine that we are we have this like this box that is of length L. So basically, this means that we have some allowed k values inside this box that now are really now, since we have a finite system, are going to be discrete. So now we can introduce quantization. When we start simulating inside a box, we start to have like some quantized values. Okay, and these quantized values are actually quite of course, since like this L, it's a crystal, so it's a big crystal. This L is going to be very big, and so the distance between these two is going to be very small. So it's something that is almost continuous, but since we have a finite box, it's going to only some states are going to be allowed, as your colleague was pointing at the beginning, saying, okay, so like in many systems we have quantized states. Okay, so basically, since we have this big box, we need to count how many available states we have in every part of this in every part of the space. Okay, and so since the thing that I want to consider is really a sphere in k space of volume of radius k. Okay, and now what I want to bring home is try to count how many, given a little bit of an increase in this volume k, how many states I can find inside this small volume. Okay, so the idea would be to count the number of states for a 3D system. The idea would be to take this sphere at a particular wave vector k. Okay, and it doesn't matter, since it's a sphere, it doesn't matter which direction exactly I pick. Okay, and then in order to count the number of states, I'm going to increase this sphere by a tiny little bit. Okay, and with this increase of the sphere shell, okay, so like we go from k to k plus dk, I'm going to count how many states fall into this increase of the shell. Okay, so let me try to see if I can use some toggle chalkboard, not canvas maybe. Okay. Okay, so can you see the sketch? Can you see me sketch? Can you see? Probably, right?
Yes, we can see it.
Perfect.
Yes. Oh.
Perfect. Okay, so basically, so the idea, as I said, is we have a sphere. We need to increase slightly the sphere and count how many states we add by this increase. Okay, so we are on a sphere. Okay, so like the area of a sphere is 2 pi. We have a sphere in k space. So here I am very slow for some reason, so I cannot write very well. But here, hopefully, you can understand that. So this part here, this is just the area of a sphere in k space, and then we increase this area by an amount dk. Okay, so this basically means that the sphere gets like a little bit of a kick towards the outside direction, and this makes it slightly bigger. Okay, now then we have like a factor of 2 here, and this factor of 2 comes from spin. So every point can host a spin up or a spin down electron, and then we have this denominator part, and this denominator part just means this is just the smallest volume that one can simulate in in our simulation box. So the idea is that we get so if we increase the sphere, so if we take like a tiny increase in the shell and we divide it by the number of by the smallest volume possible that we can describe, then what we have is the number of states in that particular shell. Okay. So and then if we simplify things, we get to this formula. We get to this formula here. And the important thing here is just that the number of states in a shell, the number of states increases as k squared times an increase in decay. Is this clear? Is there any question so far?
It's clear. Clear.
It's clear. Okay, let me go further. Okay, so then to get to the density of states, we now need to convert from K to the energy. Okay, so we had the formula from before that was looking like that we where we had the expression of the energy, and then we can extract the K. We can like move the K to the left, move the K to the left, and take the square root in order to take the K vector in terms of the energy. Now we can do like we can take the derivative. So we need a small increase in K vector. So we can take the derivative, and what this gives us is something that evolves basically with the 1 over the square root of E. So like the E here importantly is in the denominator. So what we can do now is basically substitute this expression for decay in the formula for the number of states that we have, and basically so the density of states is going to be whatever we have here divided by the it's going to be the number of states that I can have per unit energy. Okay, so it's going to be the derivative of whatever I have here with respect to energy. So the density, so this density of states that we indicate generally with G is going to be, well, here it's like a factor of normalization of the volume, but like it's really like the number of states that I have divided by the energy. And then if I do all this substitution, what I end up with is really what I end up with is really something that goes as the square root of the energy. And the reason is because like I have K squared in here. So if I have K squared, I have if I have K squared, the K squared is proportional to the energy. And then I have decay, which is proportional to 1 over the square root of the energy. So this will cancel out. And what you get out here is something that is proportional to the square root of the energy. Okay? So this basically means that for a general 3D system, for the simplest 3D systems, my density of states as a function of hopefully this is understandable. My density of states as a function of the energy is going to go to look as something roughly like this. Something roughly like this. So like something that starts like very steep and then increases slowly as the energy goes on. Okay. So let's go further. So the idea here is really like we go back to what we were introducing before. So the idea that we were looking at a 3D system here and here. So the energy is exactly the thing that we derived. For a 2D system, we get like constant steps of density of states. So like we get things that are like flat for a bunch of energies, and then you get jumps. For a 1D system, for example, for a quantum wire, we get something that goes as 1 over, so 1 over the square root of the energy. 1 over the square root of the energy, and this corresponds to these big spikes in energy that you see here, and these are called Van Hove singularity. Hopefully, I can manage to write here Van Hove singularities. And then, as your colleague correctly pointed out, when we start to go back to like a 0D system, so 0D means anything that has a finite extent. Okay, so when people talk about 0D, it doesn't really mean like no dimensions. It just means that I'm looking at something that is not periodic in any direction. Okay, so this would mean something like I don't know, like a molecule, an atom, a quantum dot, something that is like somehow contained. Okay, in that case, as I said, as your colleague pointed out before, we have a truly quantized system. So we have a situation where we have finite number of energy levels at every energy. So now the question that I might want to ask the class is really what materials that you might think of are nice example of a 3D electron gases. Okay, sorry. So like if you have in mind any feeling of the thing that we just derived, what do you think this kind of physics will be visible? What are the simplest systems that will show the physics that we have just derived together? Give a couple minutes here. Like there are many examples, okay? And feel free to look online. I mean, like I cannot see you, but like if you have from your knowledge or anything, like tell me like what you think is the like good electron gases, good examples of 3D electron gases. So remember, you need to think of a material that is maybe like I can point you in the right direction. You need to think about metallic materials that are almost where the electrons like almost don't interact with anything else.
Hello?
Hello, hi.
Hi. I guess sodium will be good for example for free electrons because they have electrons in out and out and it's not connected to the nuclei.
Yes. Okay. Absolutely amazing example. It's perfect. What maybe I can ask a question back. So like what makes sodium, like the electrons in the outer shell, all free for sodium? Okay. So what atomic shell contributes to the states? So is it the S, P, or D shell, for instance, for sodium?
I guess it is S.
S. Okay. So if it is the S shell and sodium is a good example, as you said, what other good examples do you think there are? So like, do you think that, for example, like materials that are similar to sodium will be a good example? So for instance, like
potassium and lithium.
Yeah, exactly. Yeah, very good. Yeah, exactly. Perfect. Yeah, perfectly said. So there are, okay, so this is actually the second example that your colleague pointed out. So sodium is really like it is like a very good free electron gas, as you can see here. So as you can see, like once you start having states here at -5 electron volts, like sodium is really like starts out with like something that looks a little bit like maybe this is not very beautiful, but it looks like a square root. Okay, And like the actually like most classical example, but like it's perfect. It's a material that instead of having S conducting electron, it has P conducting electrons, and this is aluminum. Okay, aluminum is actually, you can zoom in and you can really see like the behavior, which is similar to a free electron to a free electron gas. And in aluminum, you have like you really have the 2p shell that is half filled. And this makes the system like a good, good conductor. Okay, so here we have like sodium and aluminum as very good as a very good example. There are other, as your colleague pointed out. So we have the rest of the alkali metals. So if we look at potassium, also if we look at something like calcium or magnesium, they will all like have this kind of behavior where at the beginning of when you start seeing electronic states, they will behave in this with this square root with this square root behavior. But we will see that like slowly we will start to add complications and then really see how the complexity of material can emerge from. So another example that I would like to ask the class is what materials instead are a nice example of 1D electron gas. Okay, remember, so far we looked at easy bulk systems. So okay, we looked sodium, aluminum, potassium, etc. But now, okay, we need to think a little bit about dimensionalities. Okay, so the next question is going to be about 1D systems. And you like again, I ask you, like, do you like what kind of systems are good 1D electron gases?
I know that it is go in one direction, but I don't get an example in my head in right now.
What's your name, by the way? What's your name?
My name is Nihad Omar.
Me?
Nihad. My name is Nihad.
Nihad. Okay. So it goes in one direction. Maybe like I can point in some direction. Okay. So what materials do you think go in really one direction? So if you think of like all the materials that you know, okay, what materials are really long in one direction and they are confined in another direction? So for example, the materials that we looked at so far, they extend in 3 dimensions, right? It's a crystal. Okay, we want something that now is kind of crystalline-like, but only along one direction.
Maybe semiconductors or something.
Yes, some semiconductors, this is perfectly correct. So some semiconductors will go in one direction. But then, for instance, like one thing that we can think about is, for example, polymers. Okay, so polymers are this example of these long molecules where we have not really where they are periodic really in one direction. So you have these chains, okay, but they are not, of course, but like you these are really chains. Okay, so like you don't have really like another molecule going left or right. You only have a molecule going forward and backward. Okay, so something like a polymer is a good example of like a 1D systems. Okay, another system that
nanotubes, huh?
Exactly, very nice. Okay, who said this? Who is the hello? Okay, so but like you've got like a great example. So like the example here is really carbon nanotubes. So carbon nanotubes is like a system that you see here on the right. So these are tubes of carbon that are closed onto each other, and really here, so the 1D-ness, so like the wireness comes from the fact that so the electrons will be confined in the circle on the x and y direction, but along the z direction, this is basically infinite extended for. Okay. And then if you look at the density of states of carbon nanotubes, here this I've taken from like a book on physics of nanotube devices. You can really see these spikes here, right? Okay, and so these are semiconducting. The one that you see here on the left is a semiconducting nanotube. The one that you see here on the right is a metallic nanotube. But the important thing here is that whether you have a semiconductor or like an insulator, semiconductor, an insulator, or a metal, like the idea that you like the fact that you have a 1D system creates these giant spikes. So this huge accumulation of electrons in at finite energies. Okay, so here you can see really that you can engineer how many states you have in a system depending on the dimensionality, depending really on the dimensionality. Okay, so far this concludes our discussion about this concludes the discussion about density of states. We are going to go on to a completely directly related topic here, which is band structures. Okay, but like before
can I ask question, please?
Yeah, exactly. So before I go there, I would like to ask if there are any questions so that we can clear doubts and then we can go forward.
I want to ask, is alloys can be classified as first and second and third, or just like one type of elements?
This is alloys, you said, alloys.
Yeah, yes, I guess, yeah, two types of elements or more.
So depends if you have a crystalline alloy or a disordered alloy. Okay, so if you have a crystalline alloy, so this means that, for example, you have, I don't know, something like so it's like you have two types of metals, I don't know, platinum and gold, and then if this forms ordered phases, then yes, then you still have something that you can easily describe with the math that we did so far. And this will also have, we will see that in the next slides, this will also have like clear band structures and clear dispersion and so on. If you have disorder, then it becomes more complicated. Okay, so if the alloys are disordered, you can always still have a density of states. This will never go away, but other properties of the systems will be more difficult to describe. Okay, because what disorder does is that it like somehow it blurs the line between having like a periodic system and a like a molecular system. Okay, so like you have this huge system. Like in order to be able to describe something which is a disorder, you need these huge simulation boxes in order to capture the disorder. Does this make sense? Or do you want something?
Yes, I understand it. Thank you.
Okay. Any other questions so far? Like, please feel free to just ask away. Is this like a good pace? Do you want me to go slower or do you want me to go faster? Okay, so like I'll give 30 more seconds if there are any questions. Okay.
For the participants, you can also write your question on the chat. Okay.
Yeah, exactly. Feel free to ask in the chat. We have ways to read them out aloud.
There is a question by Abu Sandal. Why does aluminium approximately follow the free electron gas model?
So the reason is because this happens generally for like what I showed you is something we will see later, a system which doesn't follow this. In general, for simple systems, so system at the beginning of the periodic table or alkali metals. Let me see if I can. I can show you like a periodic table here. Periodic table. So for systems that are in this part of the periodic table here, so lithium to rubidium, beryllium to strontium here, and then systems that are in this part here of the periodic table, Generally, if they are metallic, so metallic phosphorus, metallic aluminum, the electrons tend to be more delocalized, so delocalized over the entire crystal, and so there they don't feel other electrons as much. Okay, so this means that electrons that go in spherical delocalized shells, or electrons that are metallic systems that are in at the beginning of the periodic table, like these are good examples of systems where electrons really don't interact with each other so much. Okay, so this is the reason why they are approximately free electron gas likes. Systems that generally do not obey this, we will see this later, are systems that are in this part of the periodic table. And the reason why these systems do not behave like nice electron gases is because here electrons are really much more localized inside the nucleus. So there is a clear distinction between electrons that are localized and electrons that are delocalized in systems that these are called transition metals. Okay, so if you have a transition metals, you have a separation of electrons that are in the, for example, 3D, 4D shells, and electrons that belong to other shells of the system, to S shell, or ligand, if you have like oxygen that belong to the P shell of. So this separation makes it more less like a normal electron gas. So generally, if you have like monatomic light system, or monatomic alkali metals, these they do behave very, very much electron gas like. Anything else? Okay.
Sorry, there is a question by
Please.
Nazim.
Yeah,
She
absolutely.
said, can you slow a little bit in explaining?
Of course.
Question, but she's
No, of course. No. I mean, like this is. I mean, it's good that we know at this point of the lecture. Yes. Okay. So for the next one, like I'll try to go slower. But please interrupt me. Like if you want me to go slower, then interrupt me during the lecture. Okay. So interrupt me as the lecture is going, because then I can slow down when you start when you stop understanding. Okay.
Thank you.
So anything else? Anything else that we needs to be clarified? Okay. I would say let's go forward and let's talk about band structures. Okay, so I think the canvas. So the first thing that I want to maybe discuss about band structure, maybe I can copy this in the chat so that people that can play around with this a little bit. Let me just quickly copy, and you will have access to the slides as soon as the lecture finishes. So let me just copy this in chat. Okay. So the first thing that I want to look at you is a little bit this applet. This is from the University of Colorado, and then to basically show a little bit why bands, how bands emerge. Okay, so let's start by the simplest system. Which is like a 1D quantum well, and this is, for example, I don't know, like a simple, this is some representative system I mean, it's not like a perfect representation, but it has a lot of the physics in it of like an atom, for instance, or a quantum dot or a molecule. Okay, so they will all behave kind of the same way. Okay, so in a system, in this kind of confined system, so for a quantum well, what we have is that we have a bunch of quantized states. Okay, at certain energy levels, and as you can see, okay, so we go higher and higher, and the states become more delocalized as we go up, and then as we increase the energy, the system gets closer and closer to the edges of the to really the edges of the quantum well. Okay, so the simplest system, the simplest state here, the lowest energy, this will hold exactly two electrons for up and for down. Okay, and for a single well, this will be like one peak in the center of the well. Okay. So now the question becomes, and then tell me your expectation, and then I will show you. But what happens when I start adding wells? When I start, so instead of having only one, confined system, I have 2, 3, 4 confined, 2, 3, 4 wells all together. What do you think will happen? Remember, we have a bunch of states here. We have a bunch of quantized states here. And the question, when I ask what will happen, in a sense, is how many of these states do you think we will have once we start adding more wells? When we start adding more wells, more potential, more drops in the potential energy. So
I guess when energy comes to zero, there is no state or there is no place for electrons.
Yes, but this is in general. This is true also for the well. Let me see if I can show you the magnifying glass. So at zero, we also here really, we don't really have anything even now. Okay, so the zero here is where the purple line is. But then you can see that the big, the state here is above zero. But the question is more about how many of these states, so how many of these green lines of these available states am I going to get if I start increasing the number of wells? If you have some intuition for that. It's fine if you don't know, okay? It's just for me to understand if you have already some intuition for that. So do you think the number of states will increase or decrease if I add more quantum wells? Okay, any intuition? Anyone who is not shy? Okay, maybe let's go forward. I mean, let's show you. Okay, so this is the situation. Let's remove the magnifying glass. So this is the situation when I have more than one quantum well. Okay, so let's start from 2. Okay, so as you can see here, so if I have let's start from even 1. Let's start from 1. Okay, so now the well is tighter, so we're gonna have so for us to concentrate. So if I have a tighter well, the bound states are only, in this case, there are only 3. Okay, so let's add 1 well close to let's add one well close to the one that we have before. So what you noticed is that, what you can notice is that, like if we magnify and we go like close, really close to the to the first state here, to the first state, we see that we get two states that are really close in energy. And then if you saw, like every other state gets another twin state that is very close in energy. So in my opinion, in your opinion, what will happen if I add another well?
The number of states will be increased.
Okay, so we're going to have, so if for one well we have one, for two states we have two, for three states we're going to have, this is a very surprising, we're going to have three. Okay, so what happens in your opinion if we have 10?
I think it will be one band. They will be too close to each other.
Yeah. Okay. So let's try to see. So let's raise to 10. Okay, and then you see exactly like how your colleague pointed out. We have a lot of states that are all very, very, very close in energy. Okay. In fact, here in this part here, you're going to have exactly 10 available states. Of course, each one with spin up and spin down degeneracy. Okay. But as you can see here, or even like the excited states, you're going to have bands. You're going to have a lot of states that concentrate into very particular parts of the energy space. Okay. This is the first example of a band structure. So a band is really like a continuum of states that emerges from the fact that you start to put quantum system one close to each other. Okay, and in the limit in which we form a crystal, in the limit in which, so we put an infinite amount of these quantum wells all together to form, in this case, a 1D crystal, it will create a complete continuum of states. Okay. So the idea here is that what we showed before, was like a free electron. What we showed before was a free electron. Okay. Now here we're starting from the complete opposite end. So we're starting from, let's say, like an atom or a quantum dot, and then we're putting these quantum systems that have quantized states close together. So the idea before was that if we have a free electron, we have this continuum of states. Okay, that looks like a parabola. Now we have a situation where we start from a quantized state, and then we start to recover this continuum of states if we put a lot of these quantum systems all together, all close together. Okay, so the band structure emerge from exactly this. So they emerge from the idea of putting quantum system closer to form these crystalline structures. Okay, can I go forward? Or is there any question so far? Okay, so I will go forward. I would say we do, let's say, give me 10 more minutes and then we take a break. Okay? Yes. So, like here now, so we're talking about so a little bit more math heavy. Okay, so here feel free to stop me. But so far, so we saw that by putting like this quantum system together, we start to form these continuum of states that can be this are the first example of band structures. Okay, so really, like when we put these quantum systems together, what we are doing is that we are forming crystals. And my understanding is that you have done some some of like crystalline systems with Natasha last week. Okay, so hopefully like you can understand, relate some of this to what you did last week. So let's start to consider electrons in these crystals, and crystals are nothing else than a periodic system. Okay, so we have these potentials. That here, for instance, so the potential here is the purple line. The potential here is really this purple line. Okay, so it's basically drops of potential energy in which the electrons can get trapped into. And normally, like for example, these potential lines in a realistic system will be given by the position of the atoms, because it will have some charge and it will have some potential term that comes from the charge of the atom. Okay, so the wave function, so the Bloch theorem basically tells us that we can relate the wave function in a crystalline solid to the wave function in a free electron gas by a very, very simple way. So the wave function in a solid has the same shape, so it has the same form of a free electron gas, in the sense that it has also this complex exponential e to the ikr times a little bit of a modulation function. So this modulation function basically tells us about how the periodic wave gets modified by the potential of the periodic solid. Okay, so this UNK is just like some periodic function. Okay, so we have a periodic function that modifies really the plane wave that is available in a free solid. Okay, so this periodic function will be indexed, will have some quantum numbers. K is the same number as before, so this basically just tells you about the propagation direction, and this is called something like this is the name of this this K vector is called the crystal momentum if we are in a crystal. And this n is now a band index, and this band index basically determines exactly, so it will tell us exactly in which band we are. So if we go back to the example that we had before, here remember for the isolated system we got 3 states. So a ground state, then we get like the first excited state and a second excited state. And then if we increase the number of wells in here, we see that it gets the first state gets split into 10 possible states. So this is the first band. Then we get a second band where when the excited state was, and then we get a third band when the third excited state is. Okay, so this basically, this n quantum number determines exactly this band index. So it tells us whether we're looking at the first band, at the second band, at the third band, etc., etc. Okay. So far, so good. Any questions so far?
For
Okay.
the participant, also if you have a question, you can write it on the chat.
Let me give time, like if anyone is writing question, let me.
Okay, if there is no question, you
Okay, so let me go forward. So this is important. So like in general means that we have a crystal. Okay, so the crystal, if we have a crystal, we can take the wave function for a free electrons, and then the only thing that the Bloch theorem tells us is that this we can use the same free electron wave function modulated by this periodic function. Okay, So the next thing that we want to do is to describe this periodic function somehow. Okay, so it's periodic. It's periodic. It means that we can expand it in plane waves. Okay. So now this is the most complicated part, okay? Because you're going to see that we have two types of plane waves, okay? So the idea here now is that we take this periodic function, the function that modulates the free electron wave function, and we expand this wave function into coefficients, okay? We take the Fourier coefficient expansion of this periodic function, okay? So what this means is that we need to use another plane wave, another sum over plane waves times these Fourier coefficients in order to describe the full wave function in a crystal. Okay, so remember before we had like a free electron wave function, so we had this e to the ikr. Now we have this other modulating potential that is also periodic. Okay, and so here this is also described by something that looks like a complex exponential. Okay, so we have two complex exponentials that we can now sum together. Okay, so the full wave function in a system is described as a complex exponential with two quantum numbers, with the quantum number that stems from the bands and the quantum number that stems from the propagation vector. Okay, so here we're going to see that the full in any kind of crystal we can expand the wave function into a bunch of plane waves with coefficients that depends on two quantum numbers, that depend on the crystal momentums, on the propagation vector, and depends on the Fourier component of the modulation function. Okay, so the Bloch theorem basically allows you to say, okay, so if we want to describe any system, any crystalline system, we can expand it in terms of plane waves and the coefficients that basically tells us how much of that plane wave we can mix into the system. Okay, and the idea here is that in reciprocal, so we can have something called the Brillouin zone that you should have studied in like last week. It should have been introduced last week. And for a system, so we have let me toggle notes. Second, let me try to get some note. No. Only yellow, 1 second. Let me try to just reload here. Okay, it's not, I don't get the colored one. So the idea here is that, like, for a system, we are going to have let's say like the Brillouin zone, which will be some part of K-space that will describe this one that I've drawn. Like, for instance, for like a square system would be the Brillouin zone. So it will be, so this will be the space of K vectors that we can have, and for each of these K vectors, we're going to get these now these G vectors here. So these G vectors here. Sorry. We're going to get these G vectors here, that basically, and the combination of these two will cover the entire space of functions that we can have in our crystal. Okay. So the idea is that we go from something complicated. So we go from something complicated like a crystal, and then the Bloch theorem tells us, as I repeat once again, that we can have like a plane, like a normal free electron system times a function, periodic function. The periodic function can be expanded itself into waves. And so this means that the full wave function in a crystal for each band and for each propagation direction can be described as a wave that depends on two quantum numbers times like these coefficients that basically tell you how much of that wave you have in your crystal. Let's see what we have so far. Okay. Any questions? So this is probably the most complicated part of the lecture. Everything will be downhill from here. If so far there is anything that you want to be explained better, and and then like this would be the good moment to take a 10-minute break. Feel free also to write in the chat, to write in the...
Participant, this point is very important later in the calculation. So make sure you understand it very well. If you have any questions, something not clear, you can ask, write in the chat. Also, you can write in the WhatsApp group.
Yeah, exactly. So, like, is this too fast? Is this too...
For me, the pace is fine. For the participant, what do you think? Any?
I mean, like, so far, like, everything after this is going to be simpler, okay? So, like, here, like, let's give this as much time as it needs, and then because, like, they told me that you have done some solid states already, so I don't know what I can skip and what I need to say. Okay, so hopefully this doesn't repeat too much what you've seen already.
I guess the concept is easy, but the equations appears very difficult and complicated.
So, but like I think here, so the result, I hope the result is easy in the end, in the sense that you have basically that anything that can happen in the crystal must have a very simple form. So it's a bunch of plane waves that depend on two numbers. One number that will give you the direction and another number that will give you the band, okay, times some coefficient, okay. So this coefficient here, we will see, like, this is not like super important. Every material will have its own coefficient. But the idea would be that anything that can happen in the crystal is a sum of simple plane waves. I think this is the concept that needs to pass.
Yes, exactly. We get it. Get the concept. So in experiment, I will see just material with repeating pattern, right? But
Can you repeat?
In experiments, we can see material with repeating patterns, right? Like crystals and such.
Yes.
And mathematically, we will use these equations for describing it, right?
Exactly. So this is basically what is implemented. We will see immediately DFT. So like after the break, we will finish the band structure and we go to DFT. Okay. But the idea here is that like any DFT code will implement some version of this. So like this is exactly what is used in DFT codes to describe the material. So for the material, what you will give is basically, so the purpose of any code will be to get a potential. So to get the, let me see if I can, I mean, like, let me just draw it. Let me just draw it. It takes taking forever. But like any code will take. So we'll have the potential that comes from the atoms. Okay, so let's say that I have like an atom, like a crystal that looks I don't know, like something like this. So we have an atom here. Right, like you have the various atoms here, and each atom comes, and this is going to be periodic. I'm sorry, like I'm trying to draw with the mouse, so it's going to be it's looking horrible, but I hopefully you get the idea. So each code will get from the atoms, will get this potential, and it's going to solve the Kohn-Sham equation or the Schrödinger equation in order to find all of these coefficients. Okay, so it will know that the result is going to be like a sum of plane waves, and the only thing that the code is going to do, there is a lot of complexity in there, but like the objective is really finding these coefficients here, because these coefficients will describe the full wave function of the system, of the system. Okay.
Yes, okay. Thank you.
Perfect. Okay. So if there are no more questions, or maybe what I can do is that feel free, guys, to speak with each other in Arabic, and then I'm sure that Ala and Abu Bakr will translate, like if you feel more comfortable in asking a question in Arabic.
Yes. Sorry to interrupt you, Alberto.
Sure.
There is a question by Abu Sandan in the chat. What is
please,
the relationship between Fourier expansion and the reciprocal lattice?
Okay, so this is a very profound question, and like for me, I understood it in second or third year of my PhD. Okay, so the question is what is the relationship between the reciprocal lattice and the Fourier expansion? Okay, so basically the question boils down to what is the relationship between the k vector and the g vector in here. So like I'll try to give you my intuition for it, okay, and then tell me if it makes sense. Okay, so the numbers, they describe two different orders of magnitude of a periodic crystal. Okay, so you can imagine, so you have a periodic system, okay, and the system is periodic. So the way that we describe this mathematically is the way that we describe this system mathematically is this way. So we have basically a situation where we have like our unit cell with our like atoms in here, and this unit cell repeats, right? We have a crystal that repeats. Okay, and the idea now is that this crystal is repeating itself in two ways, in the sense that so we can look at what happens in the unit cell, but we can also think about what happens several unit cells apart. So you can see that like this crystal here will continue forever, okay? Will continue forever, and then we will continue forever, and then you will have some repetitions also. We have some repetitions as this crystal continues over space. And so basically, so you have two kind of degrees of repetition, right? Like if your crystal is extended until here, then the periodicity will impose that like the crystal until here also has its periodic image repeated. So what you will see is that you don't have only the unit cell repeating, but you have also the entire bunches of unit cell that are repeating themselves. So the crystal repeats itself, and also the unit cells repeat itself. Okay. So the idea, so you can imagine that the way that you think about it is that you have a bunch of you have a crystal that describes a bunch of unit cells, and then also this crystal repeats itself in space. So generally, these G vectors describe everything that can within one unit cell. Okay. So this means that any pattern that happens, so for example, this G vector will describe, I don't know, the emergence. If you have P states in the system, these G vectors will describe the shape of the P states that can happen in. So like I'm trying to draw nice P states, maybe failing miserably, but hopefully you get the idea. So anything that happens within one single unit cell is described by this G vector, okay? And then modulations that happen due to multiple unit cells, so that are not necessarily contained into one cell, but happen over multiple cells, they are described by the reciprocal lattice. So they are described by this K vector. Okay. So anything that now that takes this pattern and then so that makes this pattern change over multiple cells, then this will be described by this K vector. Does this make sense? Does this answer the question?
Is it clear, Abu Sandal? Okay.
It's good. Is it clear?
He said okay in the chat.
Okay, so let me repeat one last time. So the G vector basically describes everything that can happen. The K vector describes everything that happens outside the unit cell. Okay, so that happens due to the repetition of the unit cell. So G vector inside, okay, so it's a periodic pattern completely contained inside the unit cell. K vector is modulations of this pattern repeated, like modulations of this pattern over the entire crystal. Okay, so far, I would say I give you guys 10 minutes. Okay, so this means for the people that need to take a break, go get a coffee or go take a break or something. For the people that still do not understand something or feel like they would be more comfortable in asking questions in Arabic, then after the 10 minutes I go get a coffee, okay, and after 10 minutes I come back, and then if there are any questions that you guys thinking about whatever we discussed so far, if you need to ask more questions, then we will answer those questions, and then the next step will be to finish the discussion about band structure, give you more example, and then start with DFT. Okay?
Okay. There is Nihad Omar. She's raising her hand, but we
sure.
can take
Let's answer Nihad.
Okay.
Please, Mihad, ask away.
Okay, I want to ask that in this there is the assumption of free electron is not valid, right? Because we have atoms.
It's not that it's not valid, it's going to be modified. Okay? So it's going to be, so the function of the free electron is going to still be there because this part is always there, you see? But it's going to be
The plane wave, right?
Yeah, the plane wave is still there, but the plane wave is going to have a shape, and the shape is going to come from this UNK.
So the assumption will be valid, but will be modified by this.
Exactly. So it's still something that has the same periodicity of a plane wave. Shape is not going to be a simple plane wave. So it's not going to be like if you see the, oh, sorry. Like I went the other way around. So you remember a plane wave is very simple. Like a plane wave is this, has just this simple shape here. Okay. You can imagine that a Bloch function will take this shape and it will have the same periodicity, but it will not just be like a simple sinusoid. It will be something more complicated.
Okay, get it.
Okay.
Okay, thank you.
No worries.
Okay, then now we can start the break.
Break.
If there is
Yes.
any question, I can take it and then we.
Yes.
I tell you.
So for me, I go 5 minutes, I take a coffee, and then 5 minutes and I'm back, and then I can look at the questions, and then in 10 minutes we start answering. Okay?
Okay, great.
Perfect. Thank you so much.
You are welcome.
Everyone, we'll see each other very soon. Hello, here we are. Okay. Still have like 4 minutes, so please take your time. Basics. Here, and then we go.
Alberto,
Yes, sir?
hi. Can you
Hi,
please
Mara.
repeat the last part? Yeah, it's me. I don't. The last part regarding the Fourier and when you connect it to the graphical this graph.
You mean K and G space, K and that one?
Yeah. Just the
Okay.
last part.
Yes. So this is okay. So this is again, like for me, it took quite a while to understand. But the idea here is that you start from the free electron. Okay, you see, and then you have like a periodic function that changes this free electron, the plane wave. Okay, so a plane wave means that you have something that is just like you have a point in space, and then it either goes up or down,
Okay,
and then
repeat itself.
yeah, exactly. And then it repeats itself. Okay. So this going up and down is only for very simple waves. Okay. Then, like what Bloch theorem tells you is that this up and down in a crystal gets modified by the periodic potential, and so like a wave in a crystal is the same as like a wave in the free sense, just that the shape of the wave gets modified by the shape of the wave gets modified by the by some periodic function. Okay, so if you look at if you let's see, if we look at 4 images of a Bloch wave here, let's see if I can. So like actually the Wikipedia page is actually quite good, for instance. So you see, so the free electron would be this dashed line. Okay, you see this is like a pure sinusoid. Okay, pure.
Sinusoidal.
So this is a pure sine. Okay, so this is a pure sine wave. You see, and then so the crystal here is probably going to be like the crystal is going to be probably like repeating these repeating dots. You see, okay, and basically this means that so the sign, so
The shape will be
the
done
shape of
into
the
the
sine wave will
conditions.
be modified by this, like this wiggly pattern that you see here. And you see this wiggly pattern goes, so it first goes up, then it goes down, then it goes up, and then it goes down, but its envelope is decided by the by the sine wave. Okay, so the sine wave will be the k vector, so the k part, while this complicated shape inside the unit cell will be the G part. Okay, so the U of k, exactly. So this U of k. Let's see if I can find another. like another shape. Yeah, okay, so maybe this is actually quite this is also maybe quite like hopefully it makes it more understandable. So you see, so like so the free electron is this sine wave, okay? Then you have the u on k, which is full wave function. The full wave function is basically the product of these two. Okay, you see that then the full wave function is something more complicated. Okay, but Bloch theorem basically means that you can decompose it in this way. Is this understandable? Is this
Yes, very much. Yeah, thank you.
okay? Ala, should I go forward? Should I?
I would ask the participant, if you have a question, you can ask now, or you write it in the chat, or if not, then we continue. Maybe wait just 1 minute.
Yeah, sure. Ala, can you boost your microphone slightly? Can you?
You cannot hear me, or?
Like I compared to the other participants, I hear you like a little bit milder. So like I have.
Yeah, Ala, your voice is a bit low.
Okay, now you hear me well.
It's still like a little bit lower.
Maybe try to increase the.
If you can increase the mic from your side, if you can try to increase the microphone.
Okay, now do you hear me well?
It's slightly better, I think.
Okay. For the participant, you can also ask.
Yeah, participant I can hear without problems. So like just you.
Okay, we might continue now.
I would say we continue then, okay? Okay. So I know that I said there are gonna be 2 breaks, but like since it's 10:50 at the moment, let's say like I do half an hour, 40 minutes, then we do like a smaller 5 minutes break while I stay here to get any questions, and then we continue all the way to midday, okay? Whatever like your time is for you. Okay. So let's look at a little bit at what happens when. So far we looked at what the shape of the wave function is. What about the energies? Okay, and so the idea of the like what happens with the periodic potential is that remember that we had before this like this parabola shape for a free electron gas, and like what the intuition for a periodic potential, what happens in practice is that the periodic potential opens up gaps in the dispersion. So in new like since we have periods, like the periods are of the order of pi over the dimensionality of the system. Like if the system is like big, like if we have like a 1D system of periodicity A, so this will open gaps at pi over units of pi over A. So you will see here in red is basically what happens. So like the dashed line is the free periodic, so the free electron dispersion, and as you introduce the periodic potential, this splits. Okay, so the red function is the red curves that you see here is what happens when you start to have the periodic potential of a crystal. And so this opens up gaps in the beryllium. This opens up gaps in the dispersion, as you can see. So like, and we will see, depending on how we fill these gaps, the material will be insulating or metallic. So the important thing here is that since we have now a periodic function, we can refold everything into the. And I'm not going to explain what a beryllium zone here, because this you should have already had. But the idea would be that the idea would be that we have a minimal part of reciprocal space in which we can describe the system, and so all of these energies we can fold back into this smaller part of reciprocal space. So what you observe here is really that you start getting these by folding back into the beryllium zone, you start getting the first idea of what we generally talk about when we talk about bands. Okay, so like this refolded dispersion we mean when we talk about the band structure. Okay, so here the idea would be that we have these green spaces, and these are completely empty. So we have no states in there. And in between these green spaces, we have observed we can observe that we have really like available states for the systems system to occupy with electron. Okay, so this is the first idea of band structure. So let's start to think about, okay, what happens? How can we? Let's start to look at the shapes that these band structures can have. I start to think about in terms of like. And try to understand what when we have a system that is metallic or insulating. And the way that we know that a system is metallic or insulating is we know how many electrons we have in the system, because we have like certain atoms participating in the bond in forming the crystal, and each of these atoms will come with a certain number of electrons. Okay. And this means that we will have to fill all the available states with a certain number of electrons. And these states will occupy the available energy levels according to something called the Pauli exclusion principle, which means basically that one state can only host 2 electrons, spin up and spin down, and then you cannot fill anymore. You cannot fill that state anymore with any electrons. You need to go one state up to fill with a spin up and a spin down, and so on and so forth. So this, in terms, gives us the occupation of the system, which is called the Fermi-Dirac, like a Fermi-Dirac distribution. So basically, if you have a bunch of electrons that you need to fill with a certain number of electrons, these will follow this particular function, which is called a Fermi-Dirac statistic or a Fermi-Dirac distribution function. And the idea is that the filling of any electronic states will depend by the distance of that energy from something called the Fermi level, or Fermi energy, which is generally indicated as EF, or often also with the Greek letter mu. So if you look at this function at 0k, this is just a step function. So this basically means that all the electrons below the Fermi level and all electrons above the Fermi level are unoccupied. But of course, as you raise temperature, as you raise temperature here, as you raise the temperature, this will be less. This will be less. Will smoothly connect. Will start unoccupying. So as we increase temperature, we will start to deplete the states. We will start to deplete the states at lower energy and start to replenish the states at higher energy. Now the question maybe here. Let me see. Maybe this week. Yes. No. Let's do it. Let's do it now. So remember that like before we were looking at situations where the system was almost free. So we had an almost free electron gas, and then there we had a band structure that was basically unperturbed. Okay, so there we get a situation where like for like aluminum, if you remember, the states were very similar to the one of a free electron gas. If we start to have a strong scattering potential, this means a strong scattering potential means that these gaps that form, they are very large. Okay, so they become very the scattering potential changes the shape of the dispersion in very unpredictable ways, and ways that are very strong. So the idea here would be like what happens if like the scattering potential is very strong, and this happens generally more localized orbitals, as your colleague was asking before. So this means electrons that belong to the d or f shells in the system. What this will do is that it will tend to strongly localize states in certain parts of the energy space. So here we have this is going to be energy, and this is going to be also here energy, and the y-axis is the density of states, so G. So if you remember, so weak scattering potential, so this means delocalized s or p electrons, and this is a question of your colleague. So basically, what systems are free electron gases? These are generally very delocalized electrons. So these they are more electron gas-like, while systems with localized orbitals, where like the periodic potential changes the structure a lot, these are more atomic-like, and these are going to be more localized. So these are going to be more localized also in the density of states. And then what you will look at, like the difference between these two pictures, you will learn about it a lot in the very next lecture tomorrow with Professor Timrov. Okay, so here we are talking a lot about strong and weak electronic potentials, and as you saw here, we have a situation where we have basically weak electron gases are very weak potentials are very electron gas like, strong potentials are more atomic like. So here we look at a system that has kind of both situation at the same time, and this is going to be a recurring thing in the sense that in general materials are complicated. So like you will have like a combination of both behavior happening in the same material. Okay, so now I want to give you like 2-3 minutes, and the question now here is like you're looking now at copper. Okay, copper is a material which has both S and D electrons. So copper is actually, if you look at the density, if you look at the occupation of copper, I think copper is D10S1. So it means that there are 10 electrons in the D shell of copper, and then there is 1 electron free in the S shell. So the question that I want to ask you is, by looking at the density of states of copper, what states, in your opinion, are more S-like, and what states, in your opinion, are more D-like for copper? Okay, so I want to give you some, say, 3 minutes. Okay, think about it. And then by looking at exactly the picture that I'm showing you, which part of the density of states is it going to be more dominated by D-type electrons, and which part of the density of states is going to be dominated by S-type electrons? Remember that in the D shell, you have you have 10 available states, 10 states. While for the S, you're going to have only 2 states. Okay, so let's give you some time, and then we can get some of the answer from from the participants.
But please, can you move to the previous slide so can differentiate between S and D? Yes, thank you.
Can I go back? Can I go?
Yes, you can. Sorry.
Maybe I can draw it here also.
There is a question in the chat by Abu Sandal. How does energy level feeling determine whether?
I cannot hear you, Ala, very well.
Okay.
Abu Bakr, can you read it? Can you?
Yes. It's the question from Sandal, right?
Yeah.
Abu Sandal. How does energy level feeling in determine whether a material is a metal,
Like
semiconductor,
we
or
are going
in?
to see, we're going to see it like right after this. So maybe let's answer this question, and then like it's really literally the slide after this. So
Ala, I think if you go to the audio setting in your in the Zoom, just choose the same as system, the first option. That should, and then you can increase the sounds.
Okay, now I think it's better. No?
It's the same. It's very low. Sorry. Maybe you can just take your headphone, use your laptop, but we can't hear you.
So for the participants, like, do we have any answers here? Like, do we have? Just try. Like, don't worry if you get it wrong. I mean, just try. So we have like, remember, you have this density of states of copper, okay? And then we like you see that we have two parts of it. Like, so the idea would be to try to identify two parts of it. One with the more localized states and one with the more weakly dispersing states.
Can I answer?
Of course, please.
Okay, yeah, like from minus 0.5 till minus 0.4, there is S, because the number of the states are very small.
Yes.
And
Very
then
good.
it
Yes,
is,
very good.
then it is increased, I guess till 10 and above, like here, states are 10 will be D.
So these states here. So these are the D states, right?
Yes,
If I understand correctly.
yes. Yeah,
Yes.
this is RD, and from
Yes.
minus 0.5 to 0.4 will be the S.
Yes,
Here.
exactly. Yes. So these are the S states. Actually, I can already tell you that also like the S states are actually like you also have like a small S component in here. So the S states are going to be
after point like 0.25.
yes.
It is S.
Yes,
Right?
exactly. Yeah, exactly. So all of these are going to be S states. Okay, and exactly has what's your name again? What's your name?
My name is Nihad.
Mihad. So like as Mihad said, so like all the states, like this big blob here, these are going to be the D states, and this like smaller, very well dispersing blob are going to be the S states. Okay. Now, exactly. So like as Mihad pointed out, like a very good way to like start to think about these kind of systems. Okay. So here, like we had noticed that we have like 10 states. Okay. So like we need to have something that is completely occupied, that is quite high. Okay. And so this is going to be roughly good to identify 10 states. So like if we have 10 electrons in 10 states, these are going to be completely below the Fermi level. And this is a good way to identify the D states for these systems. Okay, so this is exactly...
I have a question.
Please, Bihat, like, please.
Like, you said that after a Fermi, there is no electron occupied, right?
There is no
electron occupied, right? Or not
there is no
occupation
electronic occupation. There is less, like much less electronic occupation.
Yeah, there is, but it is small, or there is not.
There is, but it is. So there is, but it is like there is like here. So basically, so at 0K there is nothing. Okay, but as soon as you raise the temperature, you start having some states in the at higher energy. Okay. So this
sketch is not at temperature 0. It's like another temperature. The sketch that I talk about.
The purple sketch is at T0, while the red sketch is at finite T.
No, I guess the other sketch that we are working on, that here, yes, the temperature here is not 0.
So the energy level is here. So this basically means that all of these states here, the states like that I am now drawing, so all of these are going to be filled. So all of these are going to be completely full. Okay, and then you have empty states in here. So the idea would be like if you zoom in here at the Fermi level, so you're going to have a density of states that is going to look something like this. The Fermi level is here in the middle. So this means that here you're going to have some states that are completely full, and then some states that are empty. So like the states that I'm shading right now, they are full. And then if you have a temperature, you start occupying a little bit the states above the Fermi level. So you see, like out of all these states, only some of them are going to be completely full.
Yes, I understand it. Thank you all.
Okay, if you have temperature 0 at Fermi,
it will be 0 here after Fermi.
Exactly. Okay. So this is exactly like Mihad pointed out. This is exactly what happens. So like here, the copper D are the ones with like the red ones that you see here, and then the S states, and there is also some small P states are going to be much more delocalized in the whole system. Okay, so metal is insulator. So as you were asking before, so what distinguishes a metal from insulator? And the answer here is actually quite easy. So this depends on the position of the Fermi level compared to the rest of the band. So if the Fermi level is in the middle of the band, then the material is metallic. So it means that you need extremely small energy in order to excite an electron from an unoccupied state to an occupied, from an occupied state to an unoccupied state. Okay, so this is the reason of having the Fermi level of a gap. It means that the energy of conduction, so the energy of exciting one electron from occupied to an unoccupied shell, is extremely small. An insulator is a different story. An insulator, the Fermi level generally falls in between a gap. Okay, So the Fermi level is in here. So the Fermi level is this thing in red. Same here for here. So the Fermi level falls in the gap. So it means that everything before the Fermi level is occupied and everything above the Fermi level is unoccupied. And so it means that you need a lot of energy to excite a system from the occupied states to the unoccupied states. The occupied states, they generally get the name of valence, and the occupied states get the name of conduction band, for instance. And so this is the main difference between metallic and insulating system. I actually have to tell you that as material scientists, we make no distinction between an insulator and a semiconductor, actually. So like a semiconductor is just an insulator with generally a small gap. Okay, so the only thing that will happen for an insulator is that the gap will be smaller than, so an insulator, the gap will be larger than a semiconductor. Okay, so this concludes the theory part, mainly the theory part. And then
I have seen.
Yes. So like here, ask away any questions. So we keep here like 2-3 minutes to ask any question, and then we go forward.
Can you go to the previous slide?
Yes.
I understand this sketch in another way. Just like an insulator, there is no states after Fermi, right? So there is no electrons, no occupational for electrons. Therefore, there will not be any.
Yeah, exactly.
Like any movement or anything. So it is insulator, and in the metal there is a lot of states, right?
Yeah, exactly. So like as soon as you try to start having a lot of states, right? You start to see here having a lot of states.
Okay. So this way is right to understand the difference between metal and insulators, right?
Yes, exactly. So maybe as usual, all of these diagrams, maybe like it's best that I do it explicitly. I mean, the x-axis is always the energy, and then the y-axis is always the density of states. Okay, any other questions so far? So let's try to really understand, like try to understand clearly what we said so far, okay? So it's best that we go back and we repeat that rather than that you guys do not understand, okay? He's also in the chat, like feel free to write in the chat and then.
So if we go back to the CU picture, we can consider CU as a metal, right? Because after Fermi, there is a.
So the Fermi level in general, this is a convention that you guys.
The state is not zero, right?
Yeah, exactly. So this is a convention that like a lot of material scientists use in general. The Fermi level, unless the Fermi level is almost always at zero. Okay, so if they don't show you the Fermi level, this happens in a lot of pictures. If they don't show you the Fermi level, generally it is taken to be the energy level at zero. So you can always shift the whole energies by a constant amount. So here Fermi level is, for instance, is zero. And then as we had correctly pointed out here, the copper is a metal because the Fermi level is exactly in the middle of a band.
Okay, thank you.
Maybe let me try to show you guys. So if I look at, let's see, let's look at some complicated material, okay? And then you were going to tell me if it's a metal or an insulator. So let's let's look at, let's try germanium. Let's see.
There is a question in the chat by Abu Sandal. How can DFT distinguish between a metal and insulator?
Yes. So basically, it's not only DFT. Okay. So any method will need will have the same distinction. So let's look at the band structure, for instance, of germanium here. This I found online. This you will get from something like DFT. Okay. And in here, the Fermi level is this dashed line here at 5, like at 5. I should be slightly higher. It should be in the middle. Okay. Should be like around here. Like, is this metallic or insulating?
Can you minimize it a little because we see it? Okay.
Maybe let me try. Let me try.
There is a band gap.
Yeah, exactly. Yes, exactly. So here, actually, like they weren't very good with the plot. So the Fermi level actually touches the band, but it's completely full. It's completely full. So this band is completely full. Let's see. Let's try to look at. Let's try to look at some other system.
I get confused because I see that always E in X coordinates. Now it's
Yeah. I mean, because for bands, generally you get it on the Y coordinate, and for the density of states, you get it on the X coordinate. Okay. So here, maybe let's look at maybe like one calculation of mine. So this, I'm sure that it's nowhere. Maybe I can show you some real DFT, calculation, and then see if I. So this is the density of states for tellurium. For tellurium, let me. Because also here it's really in the middle. Let me maybe plot it with a nicer. Let me plot it with a nicer. Let me see if I can show you some realistic some realistic calculation from like a research through research. Excuse a little bit. Okay, so This one that you see here is the density of states for elemental tellurium. Maybe let's add the okay. Maybe let's take the. So this is the density of states. So this is from a real research project, and this is done exactly with density functional theorem that we will cover like right now. And just like for you to understand, so is this a metallic system or an insulating system?
Metallic system.
This is wrong. Why is it wrong? Maybe here the gap is maybe
This
here
is zero. This is zero. You have to You have to
Maybe-
focus on the axes.
yeah, maybe this
Look,
is
where is the
again,
X? Where is the Y? Where's the zeros?
maybe here. Let me zoom in a little bit. Maybe you can even more, maybe. Okay, let's try to look at it. I've zoomed in a little bit, so maybe you can try you can try and guess again. So like the important thing is the why. Okay, so why like the answer is the answer that we give. Okay. So once again, like, is this metallic or insulating? So on the x-axis we have the energy, and on the y-axis we have the density of states.
I think because there is a gap between the conduction band and the valence band.
Yes.
So there's an insulator.
Yes, exactly. Yeah, precisely. This is really, so the Fermi level is at 0 here, like I highlighted it, and it's also there is a gap between valence band and conduction band, as your colleague correctly pointed out. So this is clearly an insulating system. Actually, like it's a semiconductor because the gap is really small. Okay, but this is exactly correct. This is exactly the kind of reasoning that you should do when you have a look at this kind of systems. I mean, the tutorials that you will see, you will exactly look at metallic or insulating system, and the way that you will recognize them will be exactly with this kind of reasoning. Okay, let me close this, and then let's start. If there are no questions, let's start talking about DFT. So any questions so far? Any other question? Okay.
I might also ask a question about the density of the state for multiple, for example, for an alloy where you have a material that consists of couple of components.
Yeah, sure.
If you can give an example of that.
Yes, so like in let me see if I can if I have an example. Like I don't have it in the slides, but like I have it in my research. So if you give me like a second, I can show you an image on how it would look like. Let's see. let's see if I can give you PDOS. Here it is. So this is like maybe like a more complicated more complicated example. Okay, so this is for lanthanum titanium 03. Okay, so the material is called lanthanum titanium 03. So we have 3 types of atoms in this material, and in this case we are going to have part of the density of states that is going to be majority oxygen, as you can see here. So the oxygen 2p are concentrated here, and these they're concentrated here. Then we're going to have titanium around the Fermi level. We're going to have so these are the titanium states, and then we're going to have also lanthanum states close, like above the titanium states. Okay. So for a more complicated systems, you're going to get more complicated plots, as you can see here. So like these are actually like this is actually like if you do study on like real materials, this is how the majority of the density states is going to look like. So you're going to have parts of the systems that are generally dominated by certain orbitals of certain atoms. Alloy, it's even more complicated because alloy in general, they are alloys because you, like for example, in substitution on alloys, it's very difficult to distinguish what exactly comes from one atom or to the other. Okay, so what you will see is that more or less in alloys, you're going to have the same kind of you're going to have a lot more admixture of different states in the same parts of the energy space. Okay, so here it's really clear, like if you look at the density of states, what is titanium, what is majority oxygen, what is lanthanum. For alloys, this is going to be less obvious, okay, because you're going to have generally as much admixture from one atom as you have from other atoms. So you're going to have like something like where, for example, the titanium and the oxygens are not very distinguishable with each other. Does this make sense?
Yes, it does make sense. Thank you. There is also Rania. She raised her hand. Rania.
In the last figure, how can we read the graph since we have electrons around the Fermi energy? We can judge the system that it is metallic.
Yes. So in general, like whenever you have a system which is metallic or insulating, the way that you do it is that you look at the density of states and you look where the DOS ends. Okay. If the DOS is really in the middle of the density of states, then you have a metallic system. Okay, like here. So like here, it's really like here the density of states really crosses one band.
It is the same for the last material you showed us.
Yes, exactly. So like that material is like complicated material because DFT gives you a metal, and then you need to do like a complicated correction to make it insulating, because the experiments show that it is insulating. But DFT, like in this material that you showed here, DFT predicts that it is metallic. Okay, because the titanium is in the middle of the Fermi energy. In the middle of the Fermi energy is really in the middle of the titanium states.
So it is metallic.
So the DFT predicts it metallic. And the material experimentally is insulating. So DFT is actually, it's one of those materials where DFT is wrong. Okay, so DFT will not. Tomorrow you will see it more with Yuri. Okay, there are some materials where DFT will predict the wrong character. Okay, and this lanthanum titanate is one of these materials where like if you, and this is why you need to understand what DFT tells you. Okay, because DFT will tell you, I think that this material is a metal, and then you will have to do more complicated things in order to make it match the experiments here.
I have opinion here. if we concentrate on this picture, the blue dots is alloy, right? And the others are the substance or the elements. If we see the Fermi level is at 0 and there it is in a band gap, it will be insulator if we concentrate on the alloy, right?
So like basically, so like the blue figure here is I don't call it an alloy. An alloy is a very specific kind of system. So like the blue figure here is the experimental real material. Okay, so it's really like it's, if you wish, the density of states from an experiment. Okay, while the other color are the material as gotten from DFT. Okay, as you can see, so the real material, the blue curve, has a gap. Okay, while DFT doesn't have a gap. Okay, so this basically is one of these materials, and this happens a lot with DFT. There are a lot of materials where DFT gets it wrong. Okay, and then you need to use corrections. You need to use complicated functionals, or like like you need to do like a more complicated treatment in order to get the physics right. Okay, but this is okay. So like the real system, you can read it the same way. So the Fermi energy is in the middle of the gap, and so the system is insulating. But DFT instead predicts a metal, because DFT predicts that the titanium states are going to be crossed by the Fermi level.
Yes, okay. I understand this. Thank you.
So this was an example for the question that you asked me. Okay. So, I mean, this is a complicated material, but like for the ones that we are going to look at, is actually much more clear whether we have an insulating or a metallic system. Okay. And also the one that you will see in the tutorials are going to be more evident. But like this is to show you that there are more complicated cases. Okay. Maybe let's close this one here. Let's concentrate on something else. Okay, for copper, this should be more evident that this is like clearly a metallic system, and the experimental is also metallic. Okay. Okay, let's go further. Let's go forward, and let's talk about DFT. Okay. So DFT. So here I'm mostly talking about Quantum ESPRESSO, and the software that we're going to use is Quantum ESPRESSO. And here you can access the website at this URL that you see here. And Quantum ESPRESSO is one of the most used codes to simulate materials from first principles. Quantum ESPRESSO.
To interrupt you, Alberto, there is a last question by Abu Sultan. What is the position of the Fermi level in the metal?
It's all the position of the Fermi level in the metal is always in the middle of the bands. So like you have some band, some density of states. The Fermi level is always in the middle for a metal, and it's in the gaps for insulating systems.
Good. It's clear. Thank you.
Okay. So Quantum ESPRESSO, key facts about Quantum ESPRESSO, it uses a plane wave basis. So it's going to be like, as you saw before, like with the Bloch theorem, it's going to be ideal to describe crystals with it. It uses something called the pseudopotentials. We don't know if we'll have enough time to cover that. And then it's a free and open source code. Okay. So as I think you saw a little bit with in the past lectures, so what we need to solve in DFT is something called the Kohn-Sham equations. So these are effective electron. This is an effective electron problems. So this means that we have our very complicated many-body electron problem, which is and then we map this complicated electron problem onto a simpler problem that is non-interacting, fictitious non-interacting electrons. And the idea is that the Kohn-Sham theorem tells us that we can have density functional theory tells us that we can build a non-interacting set of the Quantum theorem tells us that we can use this non-interacting set of electrons in order to describe the density of the real electron system. Okay, so this leads us to the Quantum equations that you see here in the most general form that we can have, and this is some Hamiltonian here, so the Quantum Hamiltonian. So this is going to be a Hamiltonian that we need to find the eigen states of. And then once again, hopefully you have seen this in the past lecture, but the idea would be to solve this Hamiltonian by finding its eigenstates. And then we repeat, basically, in practice, we do this process iteratively. So we repeat, like we guess the wave functions that we want to find. We look at the application of the Hamiltonian on those wave functions to find the density of the system. The density of the system gives us an Hamiltonian. The Hamiltonian will give us the wave function, and we repeat these cycles a bunch of times until the answer doesn't change anymore. So the idea is that we start with an initial guess of the density. The density allows us, as I said before, to calculate the effective potentials of the electron that these fictitious non-interacting electrons feel. This potential goes into the Quantum equation that you saw here. So into this equation. We need to solve this Quantum equation. We need to solve this Quantum equation and find the eigenstates and eigenfunctions and eigenvectors of these Quantum equations. From this Quantum equation, we are going to compute the electron density, and then we are going to check whether we got to self-consistency or not. We got to self-consistency or not. Whether it means that if our calculated density is the same as the initial guess. Okay, if it is, we are going to like to stop the calculation. Otherwise, we're going to iterate this a bunch of times until the answer doesn't change anymore. So the question that I want to ask you is, in your opinion, which part of this cycle here is the most expensive part in terms of computational time? So is it guessing the initial step? Is it creating the potential? Is it like computing potential, or is it solving the Quantum equation? So solving the Schrödinger equation for the non-interacting electrons.
Computing and solving.
I think solve Quantum equation.
Exactly. So this is by far the most expensive one. I'm gonna put $sign here. This part here is really the most expensive one, and this is the part where most DFT code vary. Okay, so Quantum ESPRESSO will do this part slightly differently from other DFT codes that you might have heard of, like Orca or Siesta, etc. Okay. So because all of this part is where all the technicalities, this is the most difficult part, the most expensive part, and all the technicalities enter. Okay, so the idea for us would be to expand the wave function in some basis, and then compute the eigenvectors and eigenfunction in this basis. Okay. So the choice of basis in this case is crucial. So this is where, again, like various DFT codes will vary. So Quantum ESPRESSO uses the plane wave basis. So this means that if we go back to the Bloch theorem, Quantum ESPRESSO uses exactly. So Quantum ESPRESSO basically exactly uses this expansion that you see here. So it exactly computes the coefficients of the plane waves that enter the the Bloch theorem. So like Quantum ESPRESSO uses exactly this particular basis set that we know describes very well crystals. Okay, so again, the rest I don't think we have enough time to cover this. But the idea would be that so this basis, the most important thing that there are two here. So the most important thing is that the basis is orthonormal. So it means that it's a complete basis that we can describe everything that can happen in a crystal without any complicated integrals. And another thing is that this from a more computational side, this fast Fourier transform is what allows to be extremely efficient in solving this problem. So we can exploit one of the most amazing algorithms in computer science in order to make these calculations really, really extremely fast. So the disadvantages that we have is that so this kind of basis is valid only for technically valid only for periodic system, and then we're gonna spend some time into like trying to understand what happens for non-periodic system, and also that we need a huge number of and this will introduce some limitation when we look at very localized system, because we will need like a huge number of plane waves in order to describe more localized parts of the system. Okay, so for now, I would say, so it's been 50 minutes since I started talking. So I would give 5 more minutes of break, and then we're off to the last part. But then, so like think about everything that we said so far. Okay, and then if there are any questions, I can answer those questions. Otherwise, if you need to take like a breather, like let's give us 5 minutes, and then we'll finish up here.
Okay, good. I will also ask the participant if you have a question, maybe you can also, if you would like to ask us in Arabic, and then we can translate it in English. It's also fine for us.
Also, feel free to tell them in Arabic, okay? Like if
yes.
Any other question? give a couple more minutes and then we can continue. And I would say we have around like half an hour more. Is it okay if I go until 12:15, more or less?
Yes, sure. It's okay.
Started a little bit later, so.
Yeah. So we have a question in the chat. Why
Yes.
do energy gaps appear at the Briley zone boundaries?
So, so the reason is because so basically this potential, what this potential does is that it changes the shape of this parabola. Okay, and you will see, like from quantum mechanics, what you can show is that like if you have a potential that couples two parts, so that acts in a part of the system, generally the effect of a potential is almost always to open a gap. Okay, it's almost always to like change the energies of a part of the system. Okay, and this change in energy manifests as opening up in certain points at certain points of the dispersion of space. And so like you're like from the parabola you get like a parabola with states where the potential acts, where you have some difference of these where you have some difference of the states before and after before and after that part, like that position in K space. And the idea is that when you backfold so this picture is in takes into account like the whole infinite space. But of course, since you have a periodic system, you can describe a periodic system with something called a Brilliant zone. So you can think of like this extended crystal as like a periodic system backfolded onto like a smaller part where you have everything that you can describe. So if you move if you move all of these, so basically what this means in terms of these parts here of the that are separated by the periodicity pi over a, it means that this thing here can be moved pi over a to the inside of the Brilliant and to the inside of the Brilliant zone. Okay, so you can shift them by like this wave vector and then if you do this shift for every each one of these of the components of this dispersion, they will fold back into the Brilliant zone. Okay, in this way that you see here. And so but the gaps will remain because the gaps are a feature of the energy. They're not a feature of necessarily the dispersion. Okay, so in these cases, the gaps will always remain there. So this means that the gaps that emerge at the edges, at these edges here, are going to remain in the first Brilliant zone. Hopefully, this makes sense. Does this answer the question? Does this?
Is it clear, Abu Sandal? Yes. We can still take one or two questions.
Yeah, absolutely. say 1 more minute, and then we restart. Okay, Ala, can I go further? Because I think
Yes.
okay.
Yes, you can continue, and questions will come later, or also they can also interrupt you.
Yeah, sure.
Okay.
Okay, so let's continue. Okay, so like this is a little bit of technical things, and I think you will see this in the tutorials also. So let's look at the practical sides of using like a plane wave basis for our choice of choice of how to solve the equations. So basically, as I mentioned before, so this Fourier basis comes from our ability to describe the system in terms of a Fourier coefficient expansion. Okay, so we need to think about in that way. So like, how many Wiggles can we describe with our Fourier coefficients? And in general, like what we the contribution from the Fourier components that are very high, so that describe very wiggly functions, at a certain point is no longer necessary. Okay, so in most DFT codes, we have something called an energy cutoff. Okay, so in this energy cutoff basically tells us that this is sorry, like here I wrote here I have a typo in here, but basically we neglect states that are above a certain wave vector, and this generally identifies some energy. Traditionally gets identified with the energy associated with that vector, and so this is why we call this the choice of the basis set. We call it basically the choice of the cutoff energy of the plane wave cutoff. So whenever you hear plane wave cutoff, ECUT energy cutoff, it always means the same thing, and it means that out of all the Fourier coefficients that you can use, you decide a subset of them enclosed in some sphere and in some in some sphere that determines how far you can push your basis to describe your system. Okay, and one must always check the convergence of the energy with respect to convergence in general to a lot of physical observables to the energy cutoff, as this is the parameter that for the most the parameter that controls the accuracy of the calculation the most. Okay, so you need to be able to have this circle which is big enough for you for the computed observables that you want to describe of the systems, in order for them not to change anymore. For instance, if you look at the total energy of the system, this as you increase the energy cutoff, this will saturate at some point. So it will slowly go down and down and down and down until it stops changing. It stopped changing. Here, like this is total energy. Here you can look at the energy difference. That's the same. Basically, has the same meaning. But the idea here is really to look at the difference between the previous cutoff that you have decided and the next cutoff you have decided, and then when that difference is lower than a threshold, then you know that you're convergent, and you can say, okay, so for that particular observable, we can trust it within, say, 10 to the minus 3, 10 to the minus 4, whatever your criterion is. So so far we have discussed, so as I said, like we talk a lot about in terms of Fourier coefficients. So we're always talking in terms of crystals, okay? So this means that for crystals, we're going to be able to perform a very, very good description. But what happens when we don't have periodicity everywhere? So like I can ask the participant if they can, I mean, we have already like mentioned some example of these systems, but then let's think about it more. Let's think about it in more like explicit manner. What examples of systems that you might think of, electronic systems that you might think of that are not periodic in all 3 dimensions? Okay, so a crystal is periodic in 3 dimensions, and something like aluminum or gold or copper is going to be periodic in 3 dimensions. But what about other systems that are not periodic in 3 dimensions, but are maybe periodic in 2 dimensions or 1 dimension?
You mentioned earlier the polymers.
The?
Polymers.
Polymers, exactly. So polymers is exactly one example. Carbon nanotubes are another example of a 1D system. What about 2D system? Can you think of any 2D system that, what are examples of 2D systems, for instance?
You mentioned earlier also the carbon nanotubes.
But this is 1D, so this is still
This one?
one direction. See, it's always one direction, okay? Because carbon nanotubes, they are tubes, right? Like they are long tubes that are confined in the X and Y plane, but not confined in the Z plane. But like now we think about 2D materials, okay? Okay.
Can
so
we think of graphene?
Graphene is a
Graphene.
perfect example, yes. And then there is like a much simpler example that maybe it's more difficult to think about, but once you know it, it's very easy to see. And these are surfaces of systems. Okay, so basically, graphene, of course, graphene, of course, they are 2D materials. They are sheet of materials, but also a 2D material, like a 2D system that is 2-dimensional would be, for example, a bulk surface of a system. So where you have like vacuum in here. So you have vacuum. So a crystal that you have cut in one direction. So you have vacuum in here, and then while in here you have like a bulk system. Okay. 0D system instead, as I said, like 0D just means that like they are confined in all dimensions. So this would mean molecules. So benzene, water, ammonia. But not only that, okay? So we look at situations where, so 0D systems are also like, for example, defects in solid, okay? So if I have a vacancy, if I have like a substitutional defect, these are also kind of like 0D systems. So in these cases, what we can do in order to, so the idea is that we need to be able to describe these systems in terms of some periodic counterpart that approximates the non-periodicity. So for instance, in 2D systems, we have something called a slab geometry, okay? So let's say that we want to simulate, as I said before, we want to simulate the systems where we have like a bulk, and then we have vacuum on top, okay? So the way that we simulate this with a periodic system is that we try to use a slab. So we have atoms bunched together that we try to repeat, and then we get vacuum above and below this slab, okay? And the idea is that we need to be able to converge how big the slab is, how many layers of atoms we need to simulate, and how much vacuum we need in between the layers in order to be able to simulate the surface of the system. Okay. So another example is that if we want to simulate a molecule, for instance, and we know that we can only simulate this periodic system, so how would you go about simulating a molecule in terms of vacuum? Okay. So maybe let's let participants chip in here. So remember, we have a choice of a basis that is very good for crystals, but sometimes we want to be able to simulate molecules, for instance, with this. So how do we set up the calculations in order to be able to do so? Give 1 minute. This is kind of a tricky question. We give 1 minute and then we can give the answer. Remember before, so like before for a 2D system, okay, if we look at the 2D system, we had like a bunch of atoms and then some vacuum in the Z direction, okay? Because we know, okay, so this is, we break periodicity in the Z direction, we still want periodicity in the X and Y, so we need vacuum in one direction. For a molecule, we need vacuum. Where do we need vacuum, okay, if we want to simulate a molecule? Do we need it in one direction? Do we need it in two? Do we need it in all three directions? Maybe.
Can we simulate it as an infinite well?
It's kind of, it goes kind of in the same direction. Okay, an infinite well is a very simplified version of a molecule, but the idea is that you don't want the wells to be too close to each other. Okay. So like it still needs to be periodic, okay, but you want the wells to be extremely separated from each other, okay? So maybe I can give you the answer here, okay? So like in order to engineer this separation, we want a lot of vacuum, okay, between the various molecules. For example, here we have benzene, okay? So if we have codes that are limited to simulating periodic system, we need to be in the way to simulate non-periodic system means to enlarge a lot the simulation box. Okay, for a crystal we can deal with very small simulation boxes, but for molecules we need to give space for the system to not to interact with its periodic copies. Okay, and so this basically means that so we need this vacuum here. So we need a lot of vacuum between the various molecules. This should have two vacuum, and this generally makes quantum espresso not the best choice for molecules. Okay, so it's good for anything that is periodic in at least one direction. So slabs, 2D materials, 3D materials. This is quantum espresso is going to be extremely good, and you will use it for these kind of purposes. You can also use it for some molecular system, but the price that you have to pay is the fact that you need to set up a lot of vacuum in it. So you need to waste some period, you need to waste some computational time into dealing with this vacuum. Okay. So what about defects in crystals? So here maybe I can give you the answer because we're getting almost to the end. So, but like when we have systems that break periodicity, these are not only molecules; these are also defects in crystal. Okay, and in these defects in crystal, so the price that you have to pay for breaking periodicity is we need very, very big simulation cells. Okay, so here, for instance, we have a system where we have like a line defect in a crystal, and in order to capture this line defect, what we need is a very, very big simulation cell, very, very big simulation cell. So same thing for liquids or quasi-crystal. So like if we look at a liquid system or like a disordered system, what we want to do here is that we want, in order to describe it, is that we need to have a system that is periodic, but where the cell is big enough in order to be able to simulate the disorder, in the system. Okay. So this gets me closer to the end. So like the last part of what makes Quantum ESPRESSO special is the treatment of wave functions. So the treatment of something called pseudopotentials. So let's think about first as the what happens in close to the nuclei. So as you can see, like each atom in our system enters with something with like a nuclear potential that looks something like this. That looks like a charge times 1 over the radius, so the distance from the nucleus. So this means that like each one of these, for example, for the hydrogen atom, we have like a potential that looks something like this, that is very spiky. Okay, you see that like a potential is actually infinite as you get closer to zero. And if we have a single atom, we know how to solve this. This is the solution of the hydrogen atom. So we have like a quantity, like very well separated states, one from the other. Okay. So the important thing here is that the wave functions that are associated with this Coulomb potential are actually very sharply picked near the nucleus. Okay, so they wiggle very fast, very fast close to the nucleus. Okay, and this makes the calculation could make the calculation very complicated. Okay, so this means that one needs a lot of Fourier components, a lot of Fourier analysis in order to be able to describe the part which is maybe not very interesting. It's really the part close to the nucleus that doesn't participate to chemical bonding, but it's there, and so one should, in principle, needs to describe, like, needs a lot of Fourier coefficients to describe it. So the idea is that so like in a system, in like a realistic system, this looks something like this. So we have a crystal, and we have some slow varying part between the atoms. So these are interstitial regions, and then in the middle we have this extremely wiggly part, which is the atomic core region. Okay, so and we want a way to somehow tame this extremely wiggly part. So this is a part that is maybe, from a chemical point of view, as I said before, not extremely interesting, okay? Because it's stuck there. It describes really what happens in the electrons in the nuclei. Maybe it's important for certain applications, like, for instance, nuclear magnetic resonance, NMR. Maybe those people, they really need to look inside the nucleus, okay? They need to look, so not inside the nucleus, inside the core of the atoms. But for us that are interested in material science, all the interesting part comes really from the interstitial regions, comes from the part that want to chemical bond with the rest of the system, okay? So the solution here is really to hide the complexity that comes from this very wiggly region, okay? And the idea would be to use something called pseudization, pseudo wave functions. So where we substitute the very complicated, so the very spiky potential that causes this wiggly part with a much more well-behaved pseudo potential that is much smoother, okay? And the idea is that at long distances, so far away from the nucleus, which is the part that for material science is important to us, we get the same result. So the wave function far away from the nucleus are going to be the same. However, inside the nucleus, we can neglect the details, okay? So we don't really care about the details. We can have a much smoother wave function that is better characterized and easier to deal with, okay? In the end, anyway, so like the energy of the system is going to be determined by this part here. So we don't really care about what happens exactly in the middle of the nucleus, okay? Is everything clear here? Do we have any questions so far?
I want to ask if I get it clear. You mean by the last problems, like the isolated molecule, that to perform the computations of these systems, we have to care about the convergence parameters, like the ECUT, so we
Yes.
can
Yes. So for the molecule,
decrease the Fourier.
So for the molecule, you have both the ECUT and also the vacuum. So you see here that because they break symmetry. Okay, so sorry, no, they break symmetry. They break periodicity. Okay, so you need to have some vacuum when you look at molecules. Okay, so like so that the periodic copies of the molecules, they don't interact with each other. And so this basically means that we have two things to look at. We need to look at how much vacuum we have between the molecules, but also we need to look at also this cutoff, this cutoff that we described here. So this cutoff holds for any system, not only molecules, but any system will have its own cutoff. Okay, and the cutoff basically tells you how much of how complicated the functions that I can have inside the crystal can be. Okay, so this basically means that for atoms that are that have a lot of very localized states, so D atoms, F atoms, sorry, like these Wiggles, these need a very, very high ECUT. And high ECUT, high cutoff. Okay, so this will need extremely high cutoff. Okay, while for this interstitial region, this we can be much lower with a cutoff. This is not only for molecules, but for any system. Okay, so like this depends really on the atomic states that you have in your system. So for D and F electron, this is going to be even more important. Okay, so they annoy. So since here we want a high, like for this interstitial region, we want a high cutoff. We would like a high cutoff, but this interstitial region generally is not very interesting. Okay, so it doesn't really participate in chemical bonding, which means that we don't really want to. It's something that it's very expensive in terms of calculation, but it's not very informative in terms of the properties that we want to compute. Okay, so this means that we want to have strategies in order to be able to hide away this region here from the rest of the crystal. So to be able to describe this region in a much smoother way that we know is incorrect, but we are not going to look at. So it's just a way to make the calculation simpler, because the only thing that we're interested in is really these interstitial regions in material science. So the solution here is called a pseudopotential, and a pseudopotential is really like a way, as I said before, is a way to make the potential extremely smooth close to the core. And we know that here the wave function is going to be wrong, but we are not going to be interested in it because the wave functions are going to be correct at the points where we care about. So really at the points where we have to do with chemical bonding, so that are important for material science. And so here the analogy, this I took from the lecture of Shovana. My analogy here is really like I like this analogy. The idea is that we want something for so the electrons are really like looking at the nuclei, and then they are looking at the nuclei from far away. Okay, so like the interstitial region is like looking at the nuclei from far away. And the analogy here is really like the analogy of something called a dummy cup. So these are like in some places in here, like if you want to respect the speed limit, in some places here in Europe, they will put like a cutout, so like a little bit of a cartoon of a fake cop that is taking picture of your car in order for you to slow down, okay? And the idea here is really kind of the same. Like from far away, one cannot distinguish whether it's a real thing or it's it's a real cop taking the picture of your car, or if it's like this fake carton cop. And so like the cars will slow down anyway. So the idea here is kind of the same. So if you look at from far away, we want to have something cheap that performs most of the functions that we care about, but we don't really care about the internal details, okay? As long as it does our job, it does the job, then we are happy. We're happy with it, okay? And by the way, like this thing here, you can actually buy this thing here that you see. You can actually buy this on like a lot of websites. It doesn't even cost that much. Okay, with this, it's 12:15. So I would stop here. I would like to thank you for your attention. Shukran, everyone. And then I would like to ask you if there are any questions overall.
Thank you so much, Alberto. It was a very nice lecture, very interactive, and very detailed also, the explaining. So for the participant, there is a question. Yusuf is raising his hand.
Please,
Yusuf, you can open your mic and ask your question.
Excuse me, apart from procedure position, are there any other methods or solution to handle the current electron problem in DFT calculation? This is my question.
So are there like apart from I didn't get the first part.
Pseudopotentials. Apart from pseudopotentials.
Apart from pseudopotential.
Are there any another method or solution to handle the core electron problem in DFT?
Yes.
This
so
is
you
my
have
question.
if you really want core electrons, for example, for NMRs, you can use something called all electron codes. All electron DFT. There are a bunch of codes that, for example, like these ones, Win2K or FHIMs. Okay, these are the ones that I know the most. And so these they are much more expensive, but they don't use pseudopotentials. Okay, so if you're really interested in core electron properties, so this means, for example, core electron spectroscopy, Auger, this kind of stuff, then you really need to look at Win2K, FHIMs to this all electron stuff. Any other question so far? Even about everything, okay? So feel free to ask also the beginning for things at the beginning of the lecture, okay?
You can also write your question on the chat.
Yeah, exactly.
I will read it.
And please feel free to write in Arabic if it's best for you, and then they will translate. Anyone else? I'm gonna stay here, say, like for 10 more minutes, okay? Like if you want me to answer anything, like I still have some time, so.
I think Abu Sandal, you have a question?
Thanks, Dr. Alberto, for these lectures. I have two questions. One question is why do you need an energy cutoff? And two questions, how does increasing cutoff affects the accuracy of the density functional theory?
So basically, so this comes from the fact that okay, so like if you remember, like if we go back to the Bloch theorem, okay, let's So if we look back here at the Bloch theorem, so we have basically, so we know that the full wave function is written as a sum over these G vectors of like this part here, right? This is in principle infinite. Okay, so the G vectors, like this is going to be an infinite set of wave vectors that one can throw into the equation. Okay, infinite. Okay, but of course, if we do things with computers, we cannot have an infinite amount. Okay, we need to truncate at some point. Okay, and the price that you pay by truncating is really like to describe the smallest wiggles inside the unit cell. Okay, so the bigger, very big wave vectors will describe extremely small behavior, extremely wiggly behavior in the unit cell. Okay, so this means that by truncating truncating the G vectors, you are basically saying at some point, okay, I want to stop here. Okay, I don't care about states that are more localized than this amount. So I can forget about describing states with this from this energy onwards. Okay, so the thing is, you don't want to stop too early. Okay, because if you stop too early, even like maybe like you start losing stuff that is relevant for chemical bonding. Okay, so like you need to have a good balance between how far away you go in K space, in G space, so much that your problem is computable, so your problem is efficient, is described with like you can fit that into a computer, but also you need to make sure that all the relevant physics is correctly captured. Okay, so the balance between these two things is what determines the cutoff.
Okay, is it clear, Abu Sandal?
Yes, okay.
Okay, good. Any other question from the participant, Rania? Yes, Rania.
I want to ask about the physical meaning of ECUT. Can we say it is?
So the physical meaning is the smallest wiggle that you can describe, that you want to be able to describe of the wave function. So the wave function basically, so the ECUT, like if you look at the pseudopotentials, maybe here it's more clear. So like small, like because a small g, so like if we look at a wave function with small g, it's something that is going to be like very wide in like in periodic space. But like if we want, like if we have instead like a big G, here, so here is the psi, and here is R. Like, but a big G is something that wiggles a lot more. Okay, and same thing here. So like basically, like here, if you see, like in the small region, we have something that is very wiggly, and in interstitial regions instead we have something that is much smoother. Okay, so a small g will allow us to have this wide modulation, while a big G will allow us to describe these very small wiggles. Okay, and at some point these wiggles will not be important. Okay, so at some point you can throw them away and it will not. It will because the interstitial regions that we care about are going to be made of relatively wide wiggles. Okay.
Is it related to the distance from the unit cell we are?
Everything here is inside the unit cell, so it's like big wiggles inside one cell and then small wiggles inside one cell. This is not between cell. This is not between cell. This is within one cell. So like here, you really need to think about in terms of what happens close to an atom in the cell and far away to from the atom still within the unit cell. Okay.
Okay.
Remember, I remember, like this I said before, this was complicated also for me. So the G vectors describe inside the cell, the K vector describe between cells.
I want to ask a question about this graph also. I know that RC divides this sketch, right? The intertiary region will be higher than RC, right?
Can you repeat? Higher than?
In a plate, is that higher than RC will have intertial regions, right?
Yes.
And the atomic core regions will be less than RC, right?
Yeah, exactly. Yeah, precisely.
Okay, then we want to change this to the V Busido, right? The before RC.
Yeah, exactly. So
or less
like,
than.
yeah, before RC, we want to basically like we want to have a situation where we want to use much smoother, so much less wiggly functions.
Okay, then in down, what is V is over Z over R? What is Z?
This is the simple, so this is the Coulomb, so the true potential. So we want to move to take away the true potential and substitute with the smoother potential. So Z over R is the Coulomb part.
Okay, why did we change this to V Busido?
No, we are changing. We want to do this. So the idea is we want. So the idea of the true potential is really we don't want this blue one. We want the red one.
We want the red one. Okay.
Because the red one is going to have much fewer wiggles in it.
Okay, understand it.
Good. Any question? If there is no question, we can conclude now. Okay. So everything, there is a question by Rania. Yes, Rania.
Yes, please, Rania. Please, Rania. Tell me.
Yes. For determining the value of ECUT that we have to stop at it, there is also the K vector in determining this.
I think you will see this in the tutorials. So I didn't. Yes, but like you're perfectly right. You need to also converge also for the K vectors. Yeah, you're perfectly right. I just for simplicity I left it out right now, but you also need to converge for that. You're right.
That's mean it's related to the unit cell and what is near this unit cell when we are moving in the crystal.
Yeah, exactly. Yes.
Thank you.
Okay, good. So it was a pleasure to have you today, Dr. Alberto, giving this lecture. Thank you so much. And
yes.
for the participants,
let me stop the sharing. Let me.
Rania, you still have a question?
Yeah, please. Like I'm still here until it's necessary. Please.
Sorry, I just forget to lower my hand.
Okay, good. We usually take a screenshot at the end of the lecture. So if just one moment, Abu Bakr. Abu Bakr,
can you hear? Yeah, I sorry, I was unmuted.
Also for the participant, if you want to switch on the camera, then we take a screenshot.
You have to adjust the view, sorry.
Someone is in the train.
Okay, 5, 4, 3, 2, 1.
Okay, perfect. So it was an absolute pleasure to be here. Absolutely, like if you have any questions, so let me know. I think through Musa or through Maram, we can definitely, I can definitely ask like other questions you might have. So the slides are going to be online today. Okay, so I'm going to send them today to Musa or to the folder. Okay, Ma'a salama, everyone.
Thanks a lot, Alberto. Thanks a lot.
Thank you so much.
Thank you. Thank you, Alberto. Thank you very much. Thank you.
Thank you very much.
Bye.
Bye-bye.
Thank you, everyone. Have a good day.